This one is 2.33. Here we have to go back to example 2.8, and we need to show that the radial force per unit length is given by this relationship. So this is a band which is on a drum, and there's a coefficient of friction F given there. And if you look at the free body diagram of this band and this small area element there, the forces on this are your normal reaction delta n here, your tension which is T plus delta T on this side, T on the other side, and there is this friction force which is F times delta n. So if you follow this coordinate system r and theta, and if I do the force balance in the r direction, so here we will get this delta n going outwards, which will be balanced by these two tension forces and their sine components. So T plus delta T, and the angle here is delta theta by 2, so sine delta theta over 2 plus T times sine delta theta over 2. So if you notice here, this delta T times sine delta theta by 2, this term is going to be much smaller compared to T times sine delta theta by 2. So if I combine these two and simplify, I get delta n equals to 2 times T sine delta theta by 2, and if you approximate sine delta theta by 2 by delta theta by 2, from here we get T times delta theta. So this can be written as delta n over delta theta is equals to T. So this is the first relation we got from summation of forces in the y direction. Now if you do this summation of forces in the theta direction, in theta direction we have this tension, in the negative side we have this tension, and F times delta n is also going in the negative direction. So for these tensions we are going to use the cos component there. So T plus delta T times cos delta theta by 2, that's going in positive theta, minus T times cos delta theta by 2, and then your minus F times delta n equals to 0. So here you can notice this term will cancel out with this term right here, and if you approximate your cos delta theta by 2 for small angles as 1, we get delta T is equals to F times delta n, or your delta n is equals to delta T divided by F. Now if we substitute this value of delta n in equation number 1, we get delta T divided by F delta theta is equals to T. Now rearranging this, delta T over T is equals to F times delta theta, and under the limits where theta is going down to 0, this can be written as dt over T equals to F d theta. So if I do this integration here, from starting from the left hand, which is your AD end here, this is your starting point, and we do it up to this theta angle there. So we can write this as a general value of T. Similarly, theta goes from 0 to theta there. So we can write down your ln T limit T AD T equals to F times theta. So from here you can write down T is equals to T AD e to the power F theta, and this is the result which is already given in your example 2.8. So now since we have already got a relationship for T, we can go back to your equation number 1 here, and we can use that delta n over delta theta, or when you put limit delta theta tends to 0, this becomes dn over d theta, which is equals to T, which is T AD e to the power F theta. Now on that band here, if the radius is r, this arc length here is going to be r d theta for a small d theta element there, if this angle is theta from there, right? So I can divide in this relationship both side by r. So this gives us dn over r d theta, which is per unit length change in your normal reaction force, equals to T AD divided by r e to the power f theta. And this is the result that we were supposed to derive here.